Welcome students, welcome to the thin cell lecture. So what is a thin cell? In order to meet with several requirements, the fluid are stored under pressure in pressure vessels or cells and transmitted from one place to another place through pipe. The pressure vessels are made up of cast iron, sheets, steel, non-ferrous alloys, and special material used for chemical vessels. The vessels of spherical and cylindrical are used for storing the fluid under pressure. That is, for example, you can say steam boilers, air compressors, tanks, water tank, etc. The spheres are used for containing gas under pressure. The liquid the liquid and gases causing internal pressure in a closed vessels are referred as fluids. When it's a gas, the pressure is constant in all parts of the vessel. In case of liquid, the pressure is lowest at the top and increases with the depth. So when the vessels are empty, they are subjected to an atmospheric pressure both internally and externally, and hence the resultant effect of atmospheric pressure is nil. Now the vessel or cell may be thin or thick depending upon the thickness of the plate in relation with the internal diameter. The ratio, that is T by D, is equals to 1 by 20, can be considered as the suitable line of demarcation between the thin and thick vessels or shell. Okay, so in this chapter we are going to learn about different kind of shells or vessels, that means cylindrical or spherical especially, and the different types of stresses that are generated in these vessels, that is hoop stress, longitudinal stress, shear stress, etc., etc. And also we will do some numerical on it. Okay, so let's start. First we will consider on the cylindrical shell. When the cylindrical cells are subjected to internal fluid pressures, mainly three types of stresses are generated. The first one is hoop stress or circumferential stress. Or circumferential stresses. First type of stress is in case of cylindrical shell. In case of cylindrical shells, the first kind of stress that is generated is hoop stress or circumferential stress. This kind of stress is act in tangential direction to the circumference of the shell. Second one is the longitudinal stresses. The longitudinal stresses. This kind of stresses act parallel to the longitudinal axis of the shell. And third one is the radial stresses. And this kind of stresses mainly act radially and are too small and can be neglected, and these stresses are acted mutually perpendicular to each other and are the principal stresses. Now, in case of cylindrical shells, the first stress is we have to calculate the first is the hoop stress or circumferential stress. So let's see what is the hoop stress or what is circumferential stress. This kind of stress acted tangential direction to the circumference, and also as you can see in this picture, by the failure of this kind of stresses, the cylindrical shell can be divided in in this fashion, that is this kind of troughs. Okay, in troughs kind of fashion, the cylindrical shells may divide into this kind of fashion. Okay, so the some parameters which are: small d is the internal dia, small t is the thickness of the cylinder, P is the internal pressure, that is the gauge pressure. Already you have learned in fluid mechanics what is gauge pressure. P is the gauge pressure, and sigma c is the circumferential stress or the hoop stress. Now the sigma c is acted like this. This is the sigma c. This is acted in this fashion. That is, it acted through the material. Okay, and the P pressure, the pressure P is acted internally as shown in this figure. The P pressure acted internally. P is the fluid pressure. Okay, the internal fluid pressure, and the sigma C as shown in this figure is acted like in this fashion. Okay, this is sigma C. This is the hoop stresses or circumferential stresses. The another thing is that the projected area of the cylinder, we can draw the projected area of the cylinder as this. This is the projected area. Looks like a rectangle, obviously, because it's a cylinder. Small d is the internal dia. This is the thickness, small t. L is the length of the cylinder, and capital D is the outer dia of the cylinder. So the blasting force or the pressure force must be balanced by some internal resisting internal strength. Okay, so if we can write, that is the blasting force is equals to the blasting force is equals to the resisting strength, the resisting strength. Now resisting strength. Now the so the what is bursting force? Bursting force is nothing but it's the internal pressure P into the projected area. In this figure you can see this is the P, internal pressure, and the projected area is obviously D into L is the projected area. So, small d into L is the projected area. So the blasting force must be equals to, that is P into small d into L, that is small d into L, d into L. Okay, now the resisting strength, this blasting force must be resist by the material itself. Okay, so this blasting force must be resist by the material itself. So the resistive strength is obviously equals to this stress, the material stress, or the stress coming from the material, that is hoop stress, into the area. Area means here the thickness is So that is sigma c is the hoop stress, and this thickness T into L into 2, because there is 2 cross section is present for a cylinder. If we cut a cylinder in this trough fashion, we get to this kind of section, material section. So this we can write this bursting force, that is P into dl. Once again, this bursting force, that is P into dl, that is equals to sigma c into 2 into L T, sigma c into 2 into L T. So obviously that becomes the sigma c value, the value of sigma c or hoop stress or circumferential stress becomes P into D by 2T. This is the value of hoop stress or circumferential. In case of longitudinal stresses, the longitudinal stress is sigma suffix L. This is sigma suffix L, this is a longitudinal stress. So for longitudinal stresses, the cylinder failure is like this: one single cylinder divided into 2 cylinders, that is 1, this is 2. Okay, so this kind of failure, this is the failure area, this is the failure area. So this kind of failure is due to the longitudinal stresses. Here you can see in this picture, this is a stress diagram. P is the internal pressure, small d is the internal area, T is the thickness, small t, and capital D is the outer dia. So the failure is happened in this section, that is YY section. Okay, and the cross sectional area of the cylinder is obviously like this. Is a cylinder, is a circle. So small d is the internal dia, T is the thickness. So this kind of for this kind of longitudinal stresses, the pressure on the ends, that will be equals to the resistive force or resisting force. So we can write pressure on the ends is equals to the resisting force. The pressure on the ends is equals to the resisting force. Okay, or so on the end means that is the pressure force on the end, that is pressure into the area, cross sectional area, that is pi by 4 into d square. This is the internal cross sectional area. P is the internal pressure and pi by 4 into d square is the internal cross section area. I am talking about this area, this is this circular area. P, this is the P force, this is the vertical force, P force. Okay, this kind of force is P, vertical. Okay, and this area, the internal, this circular area, the internal this circular area. Okay, this is the vertical force, this is the vertical pressure P, and this circular area. Okay, so that becomes the pressure into the area is the force on the end, or pressure force on the end. So that is equals to the resisting force, that means pi dl, pi dt into sigma L. So from where this pi dt into sigma L comes? Pi dt into sigma L is nothing but it's the area of the material, this hash area here, this hash area is the material area. Okay, pi d is the perimeter. Suppose uh, you have a rope of length L. Okay, you have a rope of length L. Now you are going to bend it in like a circle. So in this fashion. So now you have bent this rope in this fashion, in a circular fashion. So the perimeter of this rope, once again, the radius, or we can say the dia of this circle is becomes d. So the perimeter becomes 2 pi r or pi d, and this pi d is obviously is equals to the length L. Okay, because this pi d perimeter is equals to the length. Okay, and the thickness, if this rope has some thickness, that is t, so that becomes L into the, so the area, the material area, this is the material area, this thickness, suppose this thickness is t. Okay, so the area becomes, the material area becomes pi d into t, or simply L into t. Okay, this concept we are applying here, we have applied here, that is p into pi by 4 d square is equals to pi into dt into sigma L. Okay, so the value of sigma L, the longitudinal stress, becomes p into d by 4t. So the longitudinal stress becomes p into d by 4t. Now the maximum shear stresses, the maximum shear stress. Okay, so in a cylindrical shell, at any point on its circumference, there is a set of two mutually perpendicular stresses. First one is sigma c, that is hoof stress, and second one is sigma L, that is longitudinal stress, which are principal stresses, and as such the planes in which these acted are the principal planes. Okay, these stresses are acted in the principal planes. Okay, and these planes are mutually perpendicular to each other. So the maximum shear stress is found, that is tau max is equals to sigma c minus sigma L by 2. So the value becomes, the sigma c is pd by 2t minus pd by 4t by 2. So that becomes pd by 8t. This is the maximum shear stress for a cylindrical shell. This is the maximum shear stress for a cylindrical shell. Now the design of thin cylindrical shells, uh, if it's required to determine the wall thickness of a thin cylindrical shell, so that it can withstand a given internal pressure P, then we have to ensure the maximum stress developed in the cell not to exceed the permissible tensile stress, that is sigma T, of the shell material. Since the circumferential stress or hoof stress is the higher one for any kind of cell, cylindrical shell, so therefore the cell is designed on this stress basis. Okay, so mathematically we can write the sigma c, the hoof stress or circumferential stress, is less than or equals to the permissible tensile stress, or we can write the value of sigma c is PD by 2T is must be less than or equal to sigma T. Sigma T is the permissible tensile stress. Okay, or the thickness of the cylindrical shell, the thickness of the cylindrical shell is equals to PD by 2 into sigma T. This is the required thickness of the cylindrical shell for a permissible tensile stress of sigma T. Okay. Now the change in dimension of a thin cylinder shell, thin cylindrical shell, due to an internal pressure, we have assumed that pressure is P. So let's start. The 1 by m is the Poisson's ratio, that is the lateral strength to the longitudinal strength. So the direct strength, so first of all, one second, the direct strength due to sigma c, or the hoof stress or the circumferential stress, is sigma c by E, modulus of elasticity, and the direct strength due to sigma L, that is the longitudinal stress, is sigma L by E. Okay, so now the net circumferential strength, that is net circumferential strength, the net circumferential strength, that is E suffix c, okay, is nothing but the direct strength minus the lateral strength due to the direct strength. Okay, the lateral strength due to direct strength sigma L, due to direct strength sigma L by E. The the net circumferential strength is nothing but the direct strength minus the minus the lateral strength due to the direct strength sigma L by E. So the circumferential strength, that is E suffix c becomes sigma c by E minus sigma L by ME, sigma L by ME. Why this M is come? This 1 by M is the Poisson's ratio. We have multiplied this direct strength, that is sigma L by E, into that Poisson's ratio, that is 1 by M. So that becomes the lateral strength. Okay, so that means we can write again that circumferential strength is nothing but, so the circumferential strength is nothing but delta d by d. Delta d is the change in diameter by the actual dia. Delta d is a change in diameter by the actual dia, is equals to the sigma c by E minus sigma c by 2 me. Why this sigma c by 2, from where this sigma c by 2 comes? From the relation we know that sigma L is sigma c by 2, because the value of sigma c is pd by 2t, and the value of sigma L is pd by 4t. So sigma L is nothing but is equals to sigma c by 2. Okay, so by substituting this sigma L value into this expression, we get sigma c by 2 me. Okay, now we are going to take common, that is e suffix c is equals to delta d by d is equals to sigma c by e into 1 minus 1 by 2m. Okay, 1 minus 1 by 2m, or we can write that is equals to the value of sigma c is pd by 2t into capital E into 1 minus 1 by 2m. Okay, so the E suffix c, that means the net circumferential strength, that is equals to delta d by d is equals to pd by 2te into 1 minus 1 by 2m, or the change in diameter. From this expression we can write the change in diameter, that delta d, that becomes p into d square by 2t into e into 1 minus 1 by 2m. Okay, this is the expression for change in diameter. Now again, the net longitudinal strength, the first one is the net circumferential strength. Now let's find the net longitudinal strength. Net net longitudinal strength, that is equals to E suffix L is equals to change in length delta L by actual length. Change in length by actual length, delta L by L, is similar the direct strength due to sigma L and the lateral strength due to the direct strength, that is sigma c by E. So the value becomes sigma L by E minus the lateral strength due to the direct strength sigma c by E. So that becomes sigma c by me, sigma c by me. So again we are going to substitute the value of sigma c here. We can write sigma L by E minus, so sigma c is equals to 2 into sigma L, so that is 2 into sigma L by m into E. Okay, so the value becomes, that is EL is sigma L by E into 1 minus 2 by M. Okay, so E suffix L is equals to delta L by delta, that is equals to the value of sigma L is PD by 40 into E into 1 minus 2 by M. Okay, so now we can calculate, we can find the value of EL is delta L by L by substituting the value of sigma L, that is PD by 40 into E into 1 minus 2 by M. Now from this expression we can write the value of delta L, that is a change in length. So the change in length, the delta L value, change in length, becomes PD into L by 40 E into 1 minus 2 by M. This is the expression for change in length. Okay, now the original volume of the cylinder is nothing but pi by 4 d square into L, and the volume increased by is expressed as pi by 4 d plus delta d square into L plus delta L. Pi by 4 d plus delta d, is the increased in diameter, square, whole square, into L plus delta L. Delta L is the increase in length. Okay, now the volumetric strength, so the volumetric strength becomes E suffix V is equals to change in volume by the original volume. Okay, so the change in volume is nothing but the volume increased minus the original volume, so that is the pi by 4 into d plus d delta square into L plus delta L minus d square into L. Okay, this is the volume increased. Okay, pi by 4 d plus d delta square into L plus del L minus the original length, d square into L, by the original length, that is pi by 4 d square into L. Okay, so the value of the volumetric strength E suffix V becomes, so by dividing the change in volume by the original volume, we get the volumetric strength is equals to del L by L plus 2 into delta D by D, delta L by L plus 2 into delta D by D. So delta L by L is the net longitudinal strength plus 2 into circumferential strength. Okay, the volumetric strength is equals to the net longitudinal strength plus 2 into net circumferential strength. Okay, so we can write volumetric strength is equals to delta V by V, the change in volume by the actual volume, is equals to 2 into the net longitudinal strength plus 2 net longitudinal strength plus 2 into net circumferential strength. Okay, now we are going to substitute the value of these, so that becomes, that is delta V by V is equals to PD by 4t e into 1 minus 2 by m plus 2 pd by 2te into 1 minus 1 by 2m. Okay, so now the value of del V or delta V, the change in volume, becomes PD into V, PD into V by 2T into capital E into 5 by 2 minus 2 by m. Okay, so this is the expression for change in volume, delta V. Okay, so now the spherical shell, as you can see in this figure, this is the failure of a spherical shell is drawn here. Okay, so the blue color arrows are the direction of circumferential stress or hoop stress which produced, and the red one is the intensity of pressure, the direction of pressure for pressure. Okay, so for this kind of shells, we can write the bursting force. The bursting force is equals to the resisting force. So we can write the bursting force is nothing but the pressure into the cross sectional area. Since the uh, internal dia is small d and thickness is t. Okay, so pressure into the internal cross sectional internal area is obviously a circle, that is pi by 4 into d square, that is equals to the resisting force. Resisting force equals to sigma c, the circumferential stress, into the area of this material, this cross sectional this area of this section cross sectional material. Okay, the material area is pi d, pi d into t, because t is the thickness, uh, t is the thickness of the material. This is the cross section. Okay, this is a cross section of the spherical shell, and since this thickness is small t and the internal dia is small d. Okay, so the area of this hash, the hash area, the area of this hash portion, the area of this hash portion is pi dt into sigma c. Okay, because sigma c is the stress, which is the material property, so it comes from the material, so that's why there is sigma c into the area of the material. So the hoop stress for a spherical shell is becomes sigma c is equals to pd by 4t. So hoop stress for spherical cell becomes pd by 4t. Now the change in dimensions. So the strain in any diametrical plane axis is E, that is delta d by d, the change in the change in diameter by the actual diameter. So that is equals to sigma c by E minus sigma c by m into E. So that is sigma c by E into 1 minus 1 by m. So by substituting the value of sigma c, we get that is Pd by 40E equals Pd by 40E into 1 minus 1 by m. Okay, so the, or better to write, delta d by d, so the change in diameter, that is delta d, becomes p d square by 40E, p d square by 40E into 1 minus 1 by m. Okay, so change in diameter is p d square by 40E into 1 minus 1 by m. Now the volume, the original volume of a spherical shell is 4/3 pi r cube. Okay, r is the radius of the spherical shell, so that becomes pi by 6 into d cube. D is the internal dia and small r is the internal radius. So now the increased in dimension, if we write, increase in volume, that is equals to pi by 6 into d plus delta d cube. Okay, so this is the increased in volume. So the volumetric strength, that is E suffix v equals to change in volume by the original volume. So change in volume is v plus delta v minus original volume by the original volume. Change in volume minus original volume by original volume. So change in volume is pi by 6 into d plus delta d cube minus pi by 6 into d cube by original volume, pi by 6 into d cube. Okay, so this is the volumetric strength. So by calculating this volumetric strength, we get 3 into delta d by d, so that becomes 3 into E. We get the volumetric strength EV is equals to 3 into E. So we can write from this expression we can write delta V by V is equals to 3 into the value of E is nothing but P into D by 40 E into 1 minus 1 by M. So the change in volume, is becomes 3 P D by 40 E into 1 minus 1 by M into V. V is the actual volume, where V is the actual volume. So delta V is the change in volume, is equals to 3 into PD by 40 E into 1 minus 1 by M into the actual volume. Now the build up cylindrical or spherical shell. The formula derived for the circumferential stress or longitudinal stress have been obtained with some pre-assumptions that the cylindrical shell is seamless, that is the solid drawn. But in actual practice, the cylindrical shells or spherical shells of large diameter, such as boiler shells, etc., are not seamless. That means are not without joints. Okay, so but instead are built up by longitudinal and circumferential joints. The longitudinal joints reduce the resisting strength of the shell plate against the bursting, and circumferential joints reduce the resisting strength of the plate against the tearing due to the pressure on the end plates. Okay, so let we are going to assume the efficiency of a longitudinal joint, that is eta L, is efficiency for longitudinal joints. Okay, and eta C, is the efficiency for is the efficiency for circumferential joints. Okay, so in case of cylindrical shell, the bursting force is equals to the resisting force. So we can simply write that is PdL is equals to 2LT sigma C into eta L, that is the efficiency for longitudinal joints. Okay, so the sigma C becomes PD by 2T into eta L. So in actual practice, the value of sigma C becomes PD into 2T to PD by 2T into eta L. In actual practice, the value of sigma C becomes PD by 2T into eta L. Okay, so now okay, now for the second case, that means the pressure on ends, that means in case of the longitudinal stresses, the pressure force on ends is equals to the resisting force. So that becomes P into pi by 4 into d square is equals to pi dt sigma L, the longitudinal stress, into eta C, the efficiency of the circumferential joints. So the sigma L becomes PD by 4T into eta C. So in the pressure on ends, that is equals to the resisting force, that is equals to P into pi by 4 d square equals to pi dt into sigma L into eta C. So in actual practice, the sigma L value becomes PD into 4T into eta C, PD by 4T into eta C. So in actual practice, the value of sigma L is PD by 4T into eta C. Okay, so this is a longitudinal stress expression. So similarly for spherical shell, the value of sigma C, that means the the circumferential stress or hoof stress value, that is sigma C, is equals to PD by 4T into eta. Okay, for spherical shell, eta is the joint efficiency. For cylindrical shell, for spherical shell, the value of hoof stress or circumferential stress is PD by 40 into eta, where eta is the efficiency of joint. In this numerical, it says that calculate the bursting pressure for a cold drawn seamless steel tubing of 60 mm inside dia with 2 mm thickness. The ultimate strength of the steel is 380 meganewton per meter square. So we have to calculate the bursting pressure, and the ultimate strength of the steel is given, and inside the dia, the internal dia, and the thickness is also given. So let's start. So the inside dia, that means the small d is equals to 60 mm. Small d is 60 mm, so that becomes 0.06 meter. Small t is 2 mm, so that becomes 0.002 meter. Okay, now the ultimate strength, that is sigma c, is 380 meganewton per meter square, or we can write this as 380 into 10 to the power 6 Newton per meter square. Okay, so now by applying the hoop stress formula or bursting failure formula, we can write sigma c is equals to PD by 2T. Sigma c is equals to PD by 2T. So the pressure P becomes 2T into sigma suffix c by d, that is 2 into 0.02 into 380 into 10 to the power 6 by 0.06. So by calculating this, it comes near about 25.33. the bursting pressure comes 25.33 meganewton per meter square. This is the answer, 25.33 meganewton per meter square. So in this lecture we have learned about the cylindrical shell and spherical shell, and different stresses that are generated in different conditions, in circumferential case or in longitudinal case, and the different failures that will come. And we have also derived the relation between them and the change in dimensions, how the dimension is changing with the stresses. Okay, in the next lecture we will do some numerical on it. Okay, in this lecture we have already done one small numerical, but in the next lecture we will done some more numerical on it. Thank you.